All right, so y'all are in luck today. We got a fairly short lecture to close out this particular chapter. We got one more set of reactions to talk about, which are really not too crazy. Our reactions of thiols. All right. An important guiding principle here that we're going to keep in mind is that sulfur is kind of this odd element in that it is a really good nucleophile. It's got those lone pairs, it's electron rich. But unlike its counterpart in the same group, oxygen, it is an absolute crap base. So it's really good at doing these nucleophile reactions, substitution reactions, but it doesn't ever accept protons. It's a terrible base, right? So again, all this to say that it really prefers substitution reaction. All right, cool. So then if we take a sulfur nucleophile and a molecule that has a good leaving group, like an alkyl halide, all right, we're going to react this with kind of our simplest, wouldn't really be considered a thiol because it's an inorganic molecule here. This thing right here is what's called hydrogen sulfide. All right, also affectionately known as sewer gas. All right, because indeed it is the byproduct that's produced by sewage. It's got this really fantastic smell to it. Also called my favorite, stink damp. I've honestly never heard it called that in the wild, but it is fun. All right, that is sort of a trade name for that particular gas. All right, and our stink damp here is a really good nucleophile, and we have this good leaving group in our molecule here. So what we're going to see is a substitution reaction where that nucleophile attacks that electrophilic carbon and kicks off that leaving group. And now we have formed our thiol. Oh, I lied. We got to deprotonate. We'll use our bromide ion. So now we have our thiol. All right. All right, but it turns out that if you want to prepare thiols, this is a terrible way to do it. Because again, what do we say about sulfur? It's a really good nucleophile. So as soon as we create this thiol here, what is it going to do? It's just going to turn around and react with another one of our alkyl halides. The sulfur doesn't stop being a good nucleophile just because it's attached to a carbon here. And remember, whenever we're carrying out reactions, and this is something that we got to kind of remind ourselves of, because it's not always obvious when we're doing pencil and paper chemistry, is we never just take one molecule of 1-bromopropane and react it with our stink gas here. We got a whole beaker full of them, right? We got 10 to the 23 of these alkyl halides floating around, or somewhere on that order. So right after that thiol is formed, it's just going to react with another one of those alkyl halides. And so we won't end up creating a thiol. We're going to end up creating a sulfide. Right? That analogous to an ether kind of molecule here, where our sulfur is sandwiched in between these two carbons. So, great method for preparing sulfides, symmetric sulfides. Bad method if you're trying to prepare thiols. All right? Because again, sulfur is too good of a nucleophile. So we can't stop it at this step. Okay, so again, sulfur being this really good nucleophile, we can react it with an alkyl halide. That sulfur will play the role of a nucleophile and will substitute that bromine. The problem is that sulfur is still a good nucleophile in this thiol that we've created, so that's just going to turn around and react with yet another molecule of that alkyl halide to create our symmetric sulfide here. All right, so then how can we prepare a thiol? I really want to just stop at that thiol step. I don't want to keep reacting and form that sulfide. We got kind of a fancy reagent that'll help us do it. All right, this thing here is what's called thiourea. Be good and put in my lone pairs. All right, thiourea is if we take regular urea, which has an oxygen, and we replace that oxygen with a sulfur, we get thiourea. All right, urea plays like a super important role in organic chemistry. I'm not sure if you all know this story, if you were introduced to this story last semester, but first of all, urea is a byproduct of the biological process that helps get rid of nitrogen from the body. We have a lot of nitrogen-rich amino acids and our nucleotides, and when these things get metabolized, we have this nitrogen waste that we need to get rid of. We don't want to package it in ammonia because ammonia is toxic to our body, so our body packages it in this urea here, which we then frankly just pee out, and that's how we get rid of nitrogen. Okay? This molecule right here plays like a super important role in the history of organic chemistry. So, we got some time, so I'm going to give you a little fun fact history lesson. All right? So, way back in the day, this idea of chemistry did not exist, right? The idea that the world was made up of these teeny tiny building blocks, atoms, was not something that was appreciated until like 400-ish years ago, right? And it was pretty radical when they came out with that idea, because it really challenged the existing power structure, which was very much so religious-based, right? So for a long time, the explanation of why things were the way they were, why is the sky blue, what is fire made of, all that crap, had this sort of very religious base because God wanted it that way kind of logic to it, all right? And the people in charge, the people that held power, were very much so the religious figures of that time, right? So they liked that. They came up with all these brilliant ideas about how the world worked. And I'm not trying to hate on any sort of religious ideas. I'm sure it served some purpose and it sounded great, but it really was kind of a theory that was shaped for that reason, because it sounded great, because it helped to like lead your people kind of thing, right? And then we had this scientific revolution where people were like, maybe we should test these ideas out. I don't know, see if there's evidence to back these things up. And that was the scientific revolution, right? This idea that let's come up with these theories, and then we're going to design experiments to test these theories. And if it shoots it down, we're not going to take that to be true anymore. So even after that happened, even after chemistry as like science was founded, even after everybody kind of was like, okay, fine, the world is made up of these teeny tiny building blocks, atoms, we were still special. Life was still something very special, something divine. So the idea that like, sure, the rocks and the fire, that's made out of these atoms, but not us, we're special, right? And it wasn't until urea came along and we had already isolated this compound from human urine, very elementary techniques where they isolated it and grew crystals and classified these crystals based on their shape. I don't even think they could do melting point at that point in time, all right? But anyways, they got these crystals from humans, and then some dude went along and synthesized the exact same thing in the lab from the stuff that he got from the rocks and all the other crap, right? And all of a sudden it was like, you mean that what came out of the human body is the exact same as what was synthesized in the lab? Oh crap, that means that we're made of the exact same stuff as everything else, right? And that kind of birthed organic chemistry. Later on, it kind of split into biochemistry. Organic chemistry has kind of taken a wild turn away from necessarily just the reactions that occur in the human body. It's really now the study of all these covalent compounds that contain carbon, including a lot of crap that would kill us, right? I mean, you go to the organic chemistry lab, you're not exactly like winging it with your safety procedures, right? You're all decked out in your gloves and your face mask and all that, or your goggles, all that stuff, right? Anyways, though, it's sort of birthed as, and the name comes from, this sort of study of, oh crap, this is the same stuff that we're made of. And urea is responsible for kind of bridging that gap. Wonderful. Okay, now we're not even talking about urea. We're talking about thiourea. All right, cool. So thiourea is a way that we can take that same alkyl halide and if we treat it with that thiourea, and then water and sodium hydroxide, we won't get this multi-step reaction that leads to a sulfide. We will just get that thiol. All right, we're not really going to look at our mechanism other than to say, after that first step, that thiourea kind of globs itself on to this molecule. And it stays there until you proceed to that second step where you wash it off with the water and the sodium hydroxide. And you get your thiol products as well as regular old urea. Which is technically an organic molecule, but nonetheless, when we're talking about our reaction, we're going to focus on just that thiol product. I don't care about the urea that's produced. Okay, cool. So let's just see here. We're going to take an alkyl halide. And we're going to first treat it with that sewer gas. And then we're going to treat it with that thiourea. followed by that wash step of water and NaOH. All right, and everybody take a second and give me the product of these two reactions. All right, so that thiourea method is just going to take our alkyl halide and replace that halogen with that thiol group. All right, if we tried to do the same thing with our hydrogen sulfide, we would indeed create that same thiol. All right, but again, the problem is that it won't stop there. This will react with yet another molecule of our alkyl halide, and we'll get this symmetric sulfide. Okay, we're going to be good and make sure we get the same number of carbons. One, two, three, four, five, six. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Check, check. Okay. Cool. So again, sulfur is such a good nucleophile that it will be able to displace that alkyl halide. But then the thiol that we create is also a good nucleophile. That's just going to turn around and react with yet another molecule of our alkyl halide to create this symmetric thiol, symmetric sulfide, sorry. If we really want to create just a thiol, we want to stop it at that step, we're going to need to use that thiourea method. All right, so thiourea, that'll allow us to create a thiol. All right, but if we use that hydrogen sulfide or stink damp, we're going to get that symmetric sulfide. That's all I got. All right, that's it for our reactions of thiols here. Okay, just these two. Wonderful. I got nothing else for you. Enjoy your day. Oh, I will say, next class we're going to do review. We'll actually have 2 days to review this semester, this unit. So next class period we'll focus on review for alcohols, and then the day after that, Monday next week, we'll focus on review for the epoxides. Our ethers, epoxides, all that jazz. On Wednesday and Thursday.